Hi class, today's topic is going to be exponential functions. As we get started with this particular topic, we're going to be focusing on the characteristic of exponential functions as well as the graphs of these functions. So let's go ahead and get started. An exponential function is a function where the base is a constant and the exponent has your variable. And I just wrote two examples here of what those might look like. I have y equals 5 to the x, and then I have y equals 1/2 x to the x plus 3. Notice that the bases are the numbers, and then your variable, the x's, are in the exponent. And there's numerous different ways of writing exponential functions. These are just two random examples. When we talk about the graphs of these functions, we're actually going to have two kinds. We're going to have exponential growth and exponential decay, but both forms of these graphs will have what we call an asymptote, and that's what I have here in blue. An asymptote is just a line that the graph will approach but never cross, and I usually will draw those as dotted lines, so just be aware that you're going to have the graph of the function itself as well as a dotted line in your final answer. So let's get started with the exponential growth functions. An exponential growth function is going to have a base that is greater than 1. All right, and that might look something like this example here, y equals 3 to the x. The easiest thing to do in these problems when you're asked to graph them is to make a table, and then from there you can determine what your asymptote is and then find the domain and range. So I'm just going to go ahead and start by plugging in some numbers. I'm going to make my points here. So I'm going to have x and y, and I'm going to plug in positive and negative numbers. I'm going to plug in 0 to start, and I'm going to go up to 3 probably, and then I'll start plugging in some of my negative numbers in here. So if I plug in 0, I get 3 to the 0 power. Anything to a 0 power is 1. If I plug in 3 to the first, I get 3. 3 squared is 9. And then 3 to the third is 27. And if you have questions on where I'm getting those numbers, let me know. And then if I plug in negative numbers, 3 to the negative 1 is the same as 1 over positive 3 to the first. Remember, negative exponents will flip your answer. So this would become positive 1/3. And then 3 to the negative second would flip again and become 1 over 3 to the positive 2, which would be the same as 1/9. So what you notice here is that in this particular example, my positive exponents gave me whole numbers, whereas my negative exponents gave me fractions, and that's okay. So you want to just go ahead and plot those points. So we'll have 0, 1, we'll have 1, 3, we'll have 2 up to 9. And notice I plotted 327 on my grid, but 3 to 27 is way up here. So this isn't a case, or this is a case where I wouldn't necessarily want to use that point. Just having it, you know that it's going to go up very quickly. And then I can plot negative 1, 1/3, and then negative 2, 1/9. So what you notice is that this graph curves a lot. It's going to curve here very slightly, and then it hits the y-axis, and then it starts to shift up very quickly. It's really steep. So this is the shape of an exponential growth function. You might hear someone say that something's growing exponentially. That means it grows very quickly. So it starts off pretty low, and then all of a sudden it shoots straight up. So also what you want to notice from this graph is that because it's leveling out, the more negative numbers I plug in, the smaller my y value gets, but it will never become negative. You can't plug in a negative number here and get a negative answer. So this is where we come in with our asymptote. So our asymptote is going to be a dotted line that it approaches. So notice that it approaches 0, but is never going to cross it. So I'm going to draw my dotted line across the line there. So my asymptote would be the line y equals 0. All right, so it's really important that you are labeling where the dotted line goes and that you plot your points and connect them. And because we have the asymptote here at y equals 0, your black line here that I drew should not cross that dotted line, so it has to stay above it. Okay? So now we just have to figure out the domain and range. Remember, domain is the x's. So if I look at my x values here, it goes to the left forever and it goes to the right forever. So my domain is actually going to be all real numbers. And remember, you can write it out that way, or you might see it written this way. Or you could write it from negative infinity to positive infinity. Either of those would work. And then our range is the y value. So the lowest y value is 0. And it never hits 0, so we have a rounded bracket. And then it goes all the way up to positive infinity. Or you might write it as y is greater than 0, but not equal to 0, because you won't get it equal to 0. And those would be the two ways you could write the range. Okay? If you have any questions about domain and range, let me know. Graphing those points or where the asymptote comes from, make sure you ask that in class. Now, the one case you would have with these is when you have to shift. That's where it gets a little bit different. So shifting is similar to what we've already done with previous graphs in other sections. You have to pay attention to the h and the k and then the a value. And I listed here what each of those represents. So h is the horizontal shift, k is the vertical shift, and then a tells you whether or not it goes up or down, and then it also tells you if the graph is stretched or compressed, so if it gets taller or if it gets shorter. Knowing how those affect your graph makes graphing a lot easier. So if I look at my example here, all I have to do is figure out what my h, k, and a are, and that's going to help me tell where my graph is going to be. The h value in this case is going to come from this -2, so it would be h is +2, which means it goes to the right. The k value is this one, so k equals 1, which means my whole graph is going to be shifted up 1. And then the number out in front of the 2 here, that's just a 1, which means that a is 1. So this is going to be shifted to the right 2 and up 1, and then it's not going to flip or stretch or anything, okay? Now, that's also going to help me figure out where my asymptote was, because in the last example, I had y equals 3 to the x. Notice my k value was 0, which is where my asymptote was. So here, my k value is going to be 1, which is where my new asymptote is. So I'm going to draw my dotted line on y equals +1. And that means my graph is not going to cross that line. It's going to be all above it or all below it, okay? And so now we can just plug in points and figure out what we've got. So I'm going to plug in x's and y's here. I'm going to plug in 0 up to, let's see, maybe +4. We'll try that. If I plug in 0, I get 2 to the -2 plus 1. That's going to reduce to 1/4 plus 1, or 1 1/4. So I'm going to plot that. So 0, 1 1/4. I'm going to plug in +1. 1 minus 2 is -1. So I'd have 2 to the -1 plus 1, which is 1/2 plus 1, or 1 1/2. So I'll plot 1, 1 1/2. And then I could plug in 2 to this equation. So if I plug that in, get that back there. 2 to the 0 power plus 1 is going to get me 1 plus 1, or 2. So I'm going to go to the point 2, 2. And then I can plug more in. 3 minus 2 gets us 1, so 2 to the first plus 1, which would get us 3. So 3, 3. And then if I plug in 4, I get 2 squared plus 1, which will get us 5. So 1, 2, 3, 4, 5. And then if I were to plug in 5 into this, I'd get 2 to the third plus 1. That's going to get us 9. That's probably about as high as you're going to want to go. Once you start getting past 9, 10, 11, it's a lot harder to graph. So now I've got all these points. I can connect them. Do the best you can to connect them. There we go. So there's my graph. It looks exactly like the last example. It's just all shifted to the right 2 and up 1. And so now if I state my domain and my range, my domain would still be all real numbers, okay, or -infinity to +infinity if you like that way of writing it. And then my range, however, won't go below 1. So I could say it goes from +1 to +infinity, or you could write y is greater than 1. Either way. Now let's look at how we can use exponential growth in application problems. So this formula I have written here, make sure you write that down. This would be a great formula if you're wanting to calculate how much you have at the end of amount of time based on a % increase. This formula has a couple different parts to it that I want to make sure we understand. The first part is that this little a here is the initial amount, all right? The R is your rate that you grow, and it's going to be a percentage. but you want to write it as a decimal. So make sure you always put a decimal there. And then t, of course, will be your time. So this is the amount in a certain amount of time based on a certain percentage. Okay, so in this example that I got here, we're talking about the number of people in the world that use the internet. And in 2006, they did this poll, and they found that this many people, over 1 billion people, use the internet worldwide. And it says at the time, they knew that the users were growing by 19.5%. So almost 20% every year, more users were using the internet. And so it says, draw a graph showing how the number of users would grow from 2006 to 2020 if the same percentage rate was used. All we have to do is plug in the numbers we know into this formula we're given, and then we can plug in points and plot. So let's see here. I know that my initial value was that 1 million number here, so I'm going to write that out. I'm going to have my amount over time is going to be, so 1 million, let's see, or 1 billion, sorry, 20 million. There we go. Okay, so I've got the initial value, and then I know that it's 1 plus my rate. Well, my rate is 19.5%. As a decimal, that would be 0.195. So I'm going to put 1 plus 0.195 there, all to the t power, because we are talking about different amounts of time. I can simplify this, so I've got my initial value, and then times 1.195 to the t. Now, all I have to do to make my graph is plug in different amounts for time since 2006, and then I can figure out what the amount is, the number of users that we have in that given year. When you make your grid, make sure that you pay attention to your labels. In this case, my x value or my t value would be my time or my year. Okay? And then my vertical axis would be the number of users. And you also have to pay attention to the numbers you're working with and what you count by. We're talking about billions of people using the internet, so don't count by ones. In this case, maybe you count by 1 billion, 2 billion, okay, 3 billion, 4 billion, and so forth, all the way up to whatever it's going to take. That way you know it's in the correct scale. And then in years, we can count 0, 1, 2, 3, and so forth, all the way until we get to 2020. So if 2006 was the original, then in 2020, that's going to be 14 years later. And now we can just plug t in, so plug different years in, and then connect our graph to see what the growth would be. Okay, so you could go ahead and finish this, plug 0, 1, 2, 3, plug in multiple numbers, and then connect your graph, and then that would be the trend for the internet users.